Today we are going to be talking about matrix operations. By the end of this video, you should be able to add and subtract matrices, you should be able to multiply a matrix by a scalar value, and you should be able to multiply matrices. First, a matrix is a rectangular array of numbers arranged into rows and columns. A matrix is named by its dimensions. We put the number of rows first, then the number of columns. So here we have an example of a matrix. If we were going to name this matrix, we can pick a letter to represent it. I'm going to pick A. And then in the subscript, we want to put the dimensions. So we have 2 rows and 3 columns. There are some special matrices. We have a column matrix, where your matrix is just one column of numbers. If we're going to name this one, I can pick a letter. I'm going to call this matrix B, and this is a 4 by 1 matrix, because we have 4 rows and 1 column. Similarly, we have a row matrix that is just 1 row, and I can pick any letter I want to represent this matrix. I'm going to pick K. And this is a 1 by 3 matrix because we have 1 row and 3 columns. The third special type of matrix is a square matrix. It has the same number of rows and columns. I'm going to call this one S, and it is a 2 by 2 matrix. We have 2 rows and 2 columns. Our last special matrix is the identity matrix, and this is the multiplicative identity. We'll talk more about this in a future tutorial. The identity matrix is generally represented by the letter I. Since this is a 3 by 3 matrix, we could call this I, and then the subscript 3 by 3, or we could just call this I3, because it is the identity matrix for a 3 by 3. Identity matrices are always square matrices, and they have 1s down the diagonal, and everything else has a 0. Next, we want to take a look at adding and subtracting matrices. To do this, the matrices must have the same dimensions, and you just add or subtract the corresponding elements. So here we have 2 matrices. If I double check their dimensions, this is a 3 by 1 matrix, and so is this one. They both have 3 rows and 1 column, so because the dimensions are the same, we can add them together. I'm going to take this number in the first row, and I'm going to add those together. Then I'm going to take the numbers in the second row and add those together. Then I take the numbers in the third row and add those together. And that gives me my sum of these 2 matrices. Notice that this matrix also has dimensions that are 3 by 1. Next, we have a 2 by 2 matrix minus a 2 by 2 matrix. So again, we are just going to subtract corresponding elements. So first row, first column, we're going to do 1 minus 2, which is negative 1. First row, second column, we have 2 minus negative 3, which gives us 5. Second row, first column, we have 3 minus 4, which is negative 1. And second row, second column, we have 4 minus negative 1, which is 5. So that is our answer when we subtract these 2 matrices. Lastly, we have a 2 by 1 matrix plus a 1 by 2 matrix. Because these matrices do not have the same dimensions, we cannot add them together. So this is not possible because we have different dimensions. Next, we're going to take a look at scalar multiplication. This is when you have a number that is kind of like the coefficient of the matrix. If we're looking at order of operations, scalar multiplication is going to come before matrix addition or subtraction. So, in problem number 5, we have 2 times our first matrix plus 3 times our second matrix. So we are sort of distributing this 2, this scalar value, into our first matrix. So we end up with -6 and 2. Then we're going to distribute the 3 to the second matrix, and we end up with 12 and -3. Because these two matrices have the same dimensions, we can go ahead and add them together. -6 plus 12 is 6, and 2 plus -3 is -1. So our final answer is the matrix 6, -1. For number 6, we have a scalar of 1/3 that we need to multiply to every element of the first matrix. And since we are subtracting, that is also similar to having a scalar of -1. So we need to multiply the second matrix by -1. So for the first matrix, when we multiply everything by 1/3, we end up with 4, -2, and 0. And if we multiply the second matrix by -1, we have -2, 5, and -7. Because these matrices have the same dimensions, we can go ahead and add them together, and we get 2, 3, and -7. So that is our final answer. Lastly, we're going to talk about multiplication of matrices. It depends on the dimensions of your matrices whether or not you can multiply them together. If you have an m by n matrix times an n by p matrix, you will end up with an m by p matrix. It's important to note here that these two dimensions must match. If they do not, you cannot multiply the matrices together. Your resulting matrix will have these dimensions, m by p. So, we want to find the missing dimension. If we are multiplying a 2 by 3 matrix by a 3 by 1 matrix, since these two dimensions match, product will be a 2 by 1 matrix. Here, if we are multiplying a 5 by 2 matrix by some matrix and we end up with a 5 by 7 matrix, we know that these two dimensions have to match and that our resulting matrix will have these dimensions. So we ended up with a 5 by 7 matrix, so this has to be a 7. So our missing matrix is a 2 by 7 matrix. Now let's take a look at how to actually multiply matrices. Here we have a 2 by 2 matrix multiplied by a 2 by 1 matrix. So we know that we can multiply these together because these dimensions are the same, and we are going to end up with a 2 by 1 matrix. So I'm just going to go ahead and draw in a large 2 by 1 matrix. When you multiply matrices, you want to take the elements of the first row and multiply it by the first column. So I am going to multiply each of these elements by each of these elements. I'm going to take the first element in the first row, which is 2, and multiply it by the first element in the first column in the other matrix, which is 3. So I have 2 times 3, and I'm going to add that to 5 times negative 4. Then I'm going to repeat the same procedure for the next row. I'm going to take negative 1 and 6 and multiply them by 3 and negative 4. So I'm going to do negative 1 times 3 and add that to 6 times negative 4. So, if I go ahead and simplify these, I have 6 minus 20 and negative 3 minus 24, which gives me my final matrix of negative 14 and negative 27. So that is my final answer for this product. Let's take a look at another example. Here I have a 2 by 2 matrix being multiplied by another 2 by 2 matrix. These dimensions match, so I can multiply it, and I'm going to end up with a 2 by 2 matrix as my product. So I'm going to give myself some extra room here. So, to find the element in the top left of this matrix, so that is the element in the first row and first column, I am going to multiply first row times first column. So I have 3 times 2, which is 6, plus 5 times 4, which is 20. To find the element that will be in the first row and second column, I'm going to multiply the first row by the second column. 3 times negative 1 is negative 3. 5 times 0 is 0. To find the element in the second row first column, I'm going to multiply second row times the first column. So I have negative 2 times 2 is negative 4, plus 4 times 4 is 16. Then, to find the element in the second row, second column, I'm going to multiply the second row times the second column. Negative 2 times negative 1 is 2, plus 4 times 0 is 0. Then I can just simplify these, and I end up with 26, negative 3, 12, and 2. And that is our product. Lastly, we have a 2 by 1 matrix times a 2 by 3 matrix. These dimensions do not match, so we cannot find the product of these two matrices. This is not possible. We have the incorrect dimensions.